All right, in this video, we're going to be going over investigation 8.1.4. I noticed that a lot of us were absent today, so I'm just going to record this quick video just so that everyone who's absent can go over the problems. Okay. So for the first one, here we're going to be looking at some real-world examples of interest rates. So our first example is going to be something called simple interest. So here, can you guys make a prediction? Do you think simple interest or compound interest is going to earn us more money? So again, this is just a prediction. All right, you can think that I think simple will earn more, or you can think compound will earn more. Just make a guess, and then we'll figure it out on the next couple of pages. What's the multiplier for an 8% interest? So the way we figure that out is we take 100% and we add 8%, and then we need to change that back to a decimal. So 108 as a decimal is 1.08. So that's our multiplier. This is 100% the 1, and we're adding an extra 8% on top. Okay. So let's take a look at our first interest, simple interest. So if I look at a bond where I invest $1,000, how is this table growing? So notice I'm going from 80 to 160 to 240. So this one is growing linearly. I'm adding plus 80 each time, right? Taking 1,000 plus 80 plus 80 plus 80. So for the fourth year, if I add another 80, I'm at 1,320. Okay. So again, how did I get this 80? So again, if I'm earning 8% interest, that means I'm taking my original amount and I'm multiplying by 8%. 8%. Okay. So what's my growth rate? Again, growth rate is next divided by previous. So for the fourth year, I'm taking 1,320, dividing that by 1,000. Okay. Moving on to A part 3. So instead of compounding things simply, what if we instead of having simple interest, what if we have compound interest? So how is this table growing here? Hopefully you guys notice that we're not adding 80 each time, we're multiplying. So this one is definitely growing exponentially. The way we go forward is we take $1,000, and if I'm adding an extra 8%, that's multiplying by 1.08. So if I multiply by another 1.08, notice that we're at 1,166.4. Multiply another 1.08, we're at the next jump. So to get the fourth year, I need another 1.08. So that's going to be 1,360.49. So comparing these two bonds, which ones earn more? So let's see, this one only earns me 1,320. This one earned me 1,360. So compound interest earns more. How is this interest calculated? So for simple interest, we only earn interest on the initial amount. But for compound interest, we earn money also on our gains. So what that means is, once I earn this extra $80 here, this $80 is also earning me more interest the next time around. So before here, I'm only earning the interest based off the initial investment, this 1,000. That's why I'm only adding 80 each time. But for compound interest, I'm also earning extra money based off the interest as well. So if I earn an extra $166, this 166 is also earning me more money the next time around. So I'm also applying the interest to my gains as well. All right, B part 1. Here we have two graphs. The red graph is going to be our simple interest. The blue graph is our compound interest. Notice that this is a discrete graph. Notice how they're all separated. So the way that money works in the bank is during the year, right, the money stays constant. But at the end of each year, the money jumps up, right? Interest is added, and the amount of money jumps up. Okay, moving to the next one. So the previous example was an example of a step function. A step function can be really hard to represent. So this time we're going to use a continuous function as a model. So for the first one, notice that we started off with 1,000 for both of these. Again, depending on the type of equation, we're using different letters. Here B is our starting point, here A is our starting point. So again, depending on the equation, we have a different starting point. Different variable represents the starting point. All right, and for the first one, we're adding 80 each time. So this is our continuous graph. And here we're multiplying by an extra 8%, so times 1.08. So what's nice about these models is that we can use them to make predictions. For example, in 20 years, replace x with 20. All right, the first account will give me $2,600 in 20 years, but this next account will earn me $4,600. So why are these considered representations and not the actual thing? All right, what actually happens is that the money in the account stays the same until the end of the year. So what actually happens if I look back at the step function? In between the year, it's just a flat amount, right? It only jumps once the interest is applied at the end of the year. What this graph is saying is that in between the year is slowly increasing, which isn't true, right? If I check my bank account in like March, in the middle of the year, I don't actually have like an extra $40, right? It still should be 1,000. So it doesn't accurately represent what's happening, right? But this can be useful to predict the amount of money at the end of each year. Right? So in between, it's not really accurate, but at each endpoint, it is accurate, right? I know that after 1 year, I made this amount. After the next year, I made that amount. So it was accurate there. Okay, B4. Here we have a couple of sequences. Sequences are another way of representing linear and exponential. For example, we have an adding pattern. We thought of that as an arithmetic sequence. If we had a multiplying pattern, we thought of that as a geometric sequence. And for both of them, right, we added 80 each time, like before, multiplied by 1.8, like before. The only thing that we need to keep aware of when we have a sequence is that this isn't actually our starting point. Sequences always start with the first term, so this is the first spot. The starting point would actually be the invisible one right before it, all right? So the one before this would be 920, and the visible zero term before this would be 1,000, jump backwards, 1.08. Okay. Where is this? Sorry, there's a decimal right here. There we go. Okay. So the initial amount is 1,000 if I jump backwards, and then my multiplier is 1.08. Okay. Here we have two more sequences. Hope you notice that this first one is a multiplying pattern. So this is compound interest. Again, the multiply is next divided by previous, the next number divided by the one right before it. So my multiplier is 1.06. And the initial amount, again, is not the 7,900, it's the one right before that. That would be the 7,500, right? Again, to figure that out, I can take 7,950 and go backwards 106. And I'm actually starting at 7,500. Similarly over here, this is simple interest. I'm taking 312 divided by 300. So I'm earning about 4% interest each year. And since it's simple interest, I'm only adding that same amount. Again, I'm not starting at 300. The one right before it would be 288. Okay. Another way of looking at compound interest is by compounding quarterly. All that means is that I'm applying the interest rate not at the end of the year, but throughout the year. So I'm just using my multiplier more than once, right? So again, by the end of the 1 year, I use my multiplier at least 4 different times. So then you can think of compounded quarterly as using your multiplier more frequently. So here I'm still starting with $1,000. Right, instead of applying the 8% every quarter, right, the 8% is split up between every 3 months. So I'm multiplying by 1.02 each quarter, sorry. So, and if we kept going, again, if I take what I had before, multiply by 1.02 each month now, not each year, each month, right? I notice that this number, 1,373, is definitely a lot more than what I earned from, right, the compound interest, right? I earn a little bit more than that. So using my multiplier, using compounded quarterly, I do earn more money quickly. Okay, and that kind of makes sense, right? If I'm using my multiplier more frequently, I can be earning more money faster. Okay, so here, this is an example of simple interest because it's a straight line. Again, starting at 500, then I become 600. Next divided by previous. Okay, so that's my multiplier. So I'm earning $100 each month when I'm starting off with 500. All right, C part 3. All right, Jerry says that he has an account that makes this much. So what's his percent increase? All right, 100% plus 0.8. So this is 0.8% increase. So he's earning that every month. So for a full year, that times a full year, 12 months in the year, he's earning 9.6% every year. So his yearly multiplier, his annual multiplier would be 100% plus 9.6, which would be 109.6. But I need to change this to a decimal, 1.096. Okay, so for this account, again, I'm going to have the same multiplier, copy and paste that over. But this time I'm starting off with $500. Okay, C part 4. Let's see. Here we're asking about if we have this table that represents our earnings, what's our quarterly multiplier? So next divided by previous. So I'm earning about 3% each quarter. So my equation would be $500 to invest, 3% each quarter. So my quarterly increase is about 3%. So how much percent will I increase for the full year? So again, there are 4 quarters in a year, so 3 times 4 quarters. I'm earning 12% for the whole year, which is 100% plus 12%.